Hello friends, so today we are going to solve the questions from the year 2014, and this we are having one question from the mains and 4 questions from the advanced. And from the year 2015 we are having 2 questions from the mains and 3 questions from the advanced. So total we are going to have 10 questions. First question, it was asked in the 2014 main, and it states that assume that an electric field E 30 x square I exists in the space iota, then the potential difference VA minus V naught, where V naught is the potential at the origin and VA potential at x is equal to 2 meters is. So we are given electric field and whose direction is along x-axis, and we need to find out the potential difference. So we are given that we have an electric field which is of E 30 x square I, and we already know the relationship between our potential difference and electric field. So we can write that our dB is equal to minus E dot dl, and we can modify this equation as per the given question. Here our length will be along x direction, so therefore we can write this will be equal to a dV will be equal to minus electric field in x direction and times dx. So we can just write our dV will be equal to VA minus V naught, and this comes as integration from 0 to 2 our E of x into dx. We substitute value of our E of x, that is our 30 x square dx. Now it is simple integration. We get this as minus of 30 x square will be giving us x cube by 3, and this comes from 0 to 2, and this comes as our 10, and we are left with 2 cube, that is 8 minus 0. So this will be 8 coming as minus 80 volt. So option number C is the correct one. Option C is correct. Next question. It was asked in the 2014 advance, and it states that charges Q, 2Q, 4Q are uniformly distributed in 3 identical dielectric solid spheres 1, 2 and 3 of radii r by 2, r and 2r respectively, as shown in figure. If the magnitude of electric fields at point P at a distance r from the center of spheres 1, 2 and 3 are E1, E2 and E3 respectively, then we have to find out what will be the strength of respective their electric field, increasing, decreasing and whatever order it might be. And here we are given three spheres, sphere 1, 2 and 3. Radius for sphere 1 is r by 2, for sphere 2 is our r, and for sphere 3 is 2r. Point P is equidistant from the center. It means point P is at a distance of r from the center in all the cases. So for sphere 1, point P will be coming as outside, sphere 2 point P will be on the sphere, and sphere 3 point P will be inside the sphere, and respective charges are Q, 2Q and 4Q. So here, for first case, the electric field that is given as E1, for second sphere it is E2, and for the third sphere it is our E3. So E1 will be electric field for a point P which is outside the sphere. So we can say for sphere 1, we have point P is outside. P is outside. Therefore, we can write that our electric field E1 will be equal to KQ upon R square. Now we come to the sphere 2. P is on the sphere. On the sphere, and here the charge density is the charge is 2Q. Therefore, we get our E2 will be equal to K 2 times Q divided by R square. We can simply write it as 2K Q upon R square. That is, this is equation 1, this will be equation 2. And now we come to the sphere 3. Here point P is inside the sphere. Inside the sphere. And the charge density is, the total charge is 4Q. So in this case, we have to draw a circle which is such that this point P is exactly on the circle. So we are only interested in the charge that will be lying within this radius R. Okay, so in proportion, we can write that electric field of E3 will be equal to K total charge is of 4Q, and radius of the sphere is about 2R. So this comes as whole Q multiplied by R. That is radius of a hypothetical sphere. So this comes as, so this comes as 8. 8 goes by 4 as 2. So this comes as 1 by 2 K Q upon R square. So this is our equation number 3. Now we simply complete, you can say compare their magnitudes. Comparing 1, 2 and 3. So from here we can clearly see that our E2 will be the highest one. So we get this as E2 will be greater than our E1 and will be greater than our E3. So this is the correct sequence of the respective electric fields. So we have E2 greater than E1 greater than E3. So option number C is correct. Next question. It was asked in the year 2014 advance, and it states that a parallel plate capacitor has a dielectric slab of dielectric constant K between its plates that covers 1/3 of the area of the plates as shown in the figure. The total capacitance of the capacitor is C, while that of the portion with dielectric between is C1. When the capacitor is charged, the plate area covered by the dielectric gets charged Q1 and rest of the area gets Q2. The electric field on the dielectric is E1 and that of other portion is E2. Choose correct option or options ignoring the side effects. So in this case, we are given a parallel plate capacitor which can be divided into two parts. One is with dielectric and another one is without dielectric. With dielectric is having electric field E1, charge Q1, without E2 and charge Q2. And the area covered by this with dielectric is 1/3 of the total area of the plates. That's a given thing to us. So first of all, we are going to find out the capacitance of the plate which is consisting of the dielectric, and let us call that capacitance as C1. Okay. And without dielectric, let us call that as C2. And let us suppose D is the distance between the plates and A is the area of the plates. A is the area of plates. So first we are going to find out our C1. So we say capacitance of the portion with dielectric. With dielectric, let us suppose that is C1, which will be equal to K epsilon naught, and that let us suppose that area is A1, and for this the area is our A2. A1 and D will be same for both, and this A1 is 1/3 of the total area. So this comes as K epsilon naught A, and this is our 3 times D. Now we come to the without dielectric. Without dielectric, let us call that as C2. This C2 will be equal to K. This is air, so value of K will be equal to 0. So we get this as epsilon naught A2 divided by D, and here A2 will be equal to 2/3 of the total area, because 1/3 is of the dielectric, so obviously remaining will be our 2/3. So this comes as epsilon naught A, and this comes as 2/3 times D. Now the total capacitance will be the summation of the two, C1 plus C2, because they are in parallel. Therefore we can say total capacitance, let us call that as C, will be equal to C1 plus C2. We substitute value of C1 and C2. So we get this as C1 was our K epsilon naught A upon 3D plus 2/3 epsilon naught A upon D. So epsilon naught A upon D we can take as common, and this comes as K plus 2, and here will be our 3D. And first of all, we need to find out the ratio C upon C1, Q upon Q1 and electric field. So we find out the ratio C upon C1. C upon C1, total capacitance we just found it is our epsilon naught A, this is our 3D and K plus 2, and C1 was our K epsilon naught A upon 3D. So here this epsilon naught A 3D, epsilon naught A 3D cancels out, and this comes as K plus 2 divided by K. So option number D is correct. Option D is correct. Now we are going to find out the charge ratio. So Q1 will be equal to C1 multiplied by V. V will be the common potential because both are in parallel, and Q2 will be equal to C2 multiplied by V. So therefore the ratio Q1 upon Q2 will be equal to C1 upon C2, and C1 is our K epsilon naught A upon 3D, and C2 is our 2 by 3 K epsilon naught A upon D, and this K epsilon naught D, K epsilon naught D cancels out, and this 3 goes by 3, sorry, there is no K here, my mistake. And this epsilon naught cancels out, 3 goes away, so this comes as K by 2. So charge is our K by 2, so this option is incorrect. Now we come to the electric field. E1 will be equal to the voltage divided by the distance between the two, and our E2 will be same, voltage divided by distance. Therefore E1 upon E2 will be equal to V by D divided by V by D, which comes as 1. So we get E1 by E2 is equal to A. So option A is correct. Is correct. Next question. It was also asked in the year 2014, and it states that let E1R, E2R and E3R be the respective electric fields at a distance R from the point charge Q, an infinitely long wire with constant linear charge density lambda and an infinite plane with uniform surface charge density sigma. If E1 R naught, it should be equal A is equal to E2 R naught, A is equal to E3 R naught at a given distance R naught, then we have to find out what will be the charge relationship between E1 and E2 when the distance between is R naught by 2, and we are going to find out what will be our R naught. So we can write that our E1 electric field will with respect to R naught will be equal to charge divided by 4 pi epsilon naught, and this comes as r naught square. But in the options it is r naught by 2, so therefore we can just convert it and we can write this as even r naught by 2 will be equal to, this comes as q upon 4 pi epsilon naught, and this comes as r naught by 2 and its whole square. So we get our even at a distance of r naught by 2 is equal to 4 times q 4 pi epsilon naught, and this comes as r naught whole square. Similarly, we can find out our E2 as well as our E3. So we get our E2 r naught will be equal to lambda divided by 2 pi epsilon naught r naught, and from here we can say our E2 r naught by 2 will be equal to, this comes as 2 times lambda, and this is about 2 pi epsilon naught times r naught, and our E3 r naught will be equal to sigma upon 2 epsilon naught. So we get our E3 r naught by 2 will be equal to sigma 2 epsilon naught. Okay, and here we have to remember that E1 is the electric field because of the point charge, E2 is the electric field because of the long wire, and E3 is the electric field because of the infinite plane. Okay. So that's why all the three formulas are different. But we are given that our E1 r naught is equal to E2 r naught is equal to E3 r naught. So we substitute their values, we get q upon 4 pi epsilon naught r naught square is equal to lambda upon 2 pi epsilon naught r naught is equal to sigma upon 2 epsilon naught. And from here we can find out our charge, and the charge is given in form of our sigma. So we compare our first and last. So this gives us that our charge q will be equal to, this we have 4 pi epsilon naught and r naught square multiplied by sigma divided by 2 epsilon naught. Epsilon naught 2 goes by this 4, so we get our charge q will be equal to 2 pi sigma r naught square. So this is our charge. Okay. And the charge is given as 4, so this option is incorrect. Next we can find out of our r naught. R naught is in the terms of our lambda as well as sigma, so we are going to make a comparison between these last two. Okay. And we get from here that our lambda upon 2 pi epsilon naught r naught is equal to sigma upon 2 epsilon naught, and here this 2 epsilon naught cancels out, therefore we get our r naught will be equal to lambda upon pi sigma. So r naught is also, option B is also incorrect. Now we are going to find out what will be the magnitudes of their respective electric field at a distance of r naught by 2. So we already know that our E1 R naught by 2, and we found it was our 4 times Q and 4 pi epsilon naught R naught square, and we have our E2 one second. Okay, and we have our E2 we found out to be 2 lambda is equal to, and it was our 2 lambda, and here we have 2 pi epsilon naught multiplied by R naught. And so first option is our E1 is equal to R naught by 2 multiplied by twice E2 R naught by 2. Okay, so let us check this option. Let me write E3 also, much more easier then. So we can say our E3 R naught by 2 is equal to sigma upon 2 epsilon naught. Okay. And we already know the relationship between this sigma and Q as well as our R naught, lambda and sigma. Okay, so we are going to use all these relationship. Let us call this as 1, this as 2, and this entire equation let us call as 3. So you can say from equation, all these equations are 3, so you can say from 1, 2 and 3 we get that our E1 R naught by 2 will be equal to 4 times E1 times R naught, and that is equal to twice E2 R naught by 8. And next is our divide E2, so we can say E2 upon R naught by 2 will be equal to, this comes as twice E naught R naught, which is equal to twice E3 R naught by 2. Therefore, you can say that our E2 R naught by 2 and we have our E1 R naught by 2 is equal to, one second, check if these options are correct or not. there is some, yes, this is 2. So therefore this option number C is correct. C is correct. Next question. It was asked in the 2014 advance, and it states that 4 charges Q1, Q2, Q3 and Q4 of same magnitude are fixed along x-axis at -2, -a, plus 2, plus 2a. A positive charge Q is placed on the positive y-axis at a distance b greater than 0. 4 options of the sign of these charges are given in column 1. The direction of the forces on the charge Q is given in column 2. Match column 1 with the column 2. Select the correct option using the code given below in the list. So we are given that Q1, Q2, Q3 and Q4 are the charges which are fixed at -2, -a, plus a and plus 2a, and the charge plus Q is fixed at a position B, and we have to find out the force based on given options. So first option states that Q1, Q2, Q3 are all positive. Okay. So we are only interested in their directions, not in magnitude. So for option A, we are given that Q1, Q2, Q3 and Q4, these all are positive, and the charge Q which is at B is also positive. So because of that, there will be a repulsive force acting on them. Okay. Therefore we can just draw an approximate figure for that, and we have charge Q1, charge Q2, then we have Q3, and then we have Q4, and this is our plus Q. So here all these charges are positive. So because of that, the electric field at this positive charge because of Q1 will be in this direction. Let us call this as E1, and because of our Q2, it will be in this direction. Let us call as E2. Similarly, we are going to have for E3, and finally for our E4. And we can divide these electric field into respective components. For that, let us draw this point here. So we are having E1. So E1 is going to have two components. One will be our E1x and the other one will be our E1y. Similarly, we are going to have our E2. Once again, two components. It will be have our E2x and it will be our E2y, and from other side also this is our E3, so this will be our E3x and we are having E3y, and finally we are having E4. So we have our E4x and we have our E4y. So all the x component will cancel each other. So net electric field will be along y-axis. Okay. Therefore, we can say that this will be our plus y. And for option number A, it will be our, that is P is going to give us, option A is going to give us as R, that is plus. So this will be R. Okay, so B and D cannot be correct. Only option possible are A and C. In the second part, we are given that Q1 and Q2 are positive, Q3 and Q4 are negative. Okay. So B, there is no need to sort it out because B states that it is only with respect to P. Okay. So this is our for sure P. The only difference is for now C and D. So let us start with C. And C states that we are having Q1 and Q4 positive, Q2 and Q3 negative. Okay, let's directly solve for option C. And we have this as our Q1, Q2, Q3 and Q4, and this is our plus Q. And it says that Q1 and Q4 positive. So this is positive, Q4 is also positive, and other two are negative. Now similarly, we can, for Q1, we are going to have in this direction, let us suppose that is our E1, and for our Q2, it will be in this direction, let us suppose that is our E2. Okay. Similarly, for our E3 also, so this is our E3, and then we have our Q4, which will be in this direction, that is our E4. So once again, we can just redraw this entire force structure with respect to their divisions. So we have our E1. So E1, we are going to have our E1x, and we are going to have our E2x, sorry, E1y. Next is our E4. So this is our E4. E4, we are going to have E4x, and it will be our E4y. And our E2 is along this axis. So we are going to get this will be our E2x minus x obviously, and this will be our, sorry, E2y. And this will be our E2x, and this we are going to get and this is our E3. So E3, once again, this will be our E3x, and here we are going to have our E3y. And Q1, Q4 positive, Q2, Q3 negative. Oh, yes. So from here the net will be along our y-axis, which is a negative axis. Okay. So therefore this option C is going to give us a S. Okay. So option number A is the correct option. Okay. So option A, this gave us plus, which is equivalent to our R option, and option C gave us minus of y. This gives us minus y, which is equivalent over S. So option A is the correct one. Option A is correct. Next question. It was asked in the 2015 mains, and it states that in the given circuit, charge Q2 on 2 microfarad changes as C is varied from 1 microfarad to 3 microfarad. Q2 as a function of C is given properly. The figures are drawn schematically and not to the scale. So we have to find out how the variation of C capacitance is going to affect the charge Q2. Basic circuit is given to us. Applied EMF is E. We have a capacitance C, whose capacitance is being varied between 1 and 3 microfarad. And we have two capacitors. That is our, let us suppose this is our C1 and this is our C2. Charge on C2 is given as Q2. Okay. For C1, let us suppose the charge is our Q1. And we assume, let us suppose there is this point is called as a point number A. So we can say that our if charge on C is given as QC, then we can write that, suppose charge on C is given as QC and charge on C1 is given as Q1 and charge on C2 is given as Q2. Therefore, we can say that our QC will be equal to Q1 plus Q2. And at this point A, let us suppose the potential is V. So on the one side, the potential is our E, and on the other side of capacitor C, the potential is is V. Therefore, we can write for QC, this will be equal to, charge QC will be equal to C, and the potential difference, that is E minus V, is equal to, and other side is obviously equal to 0, so this will be 0. So therefore the potential across C1 will be equal to V minus 0, and potential across C2 will be also over V minus 0. So therefore we get our Q1 will be equal to C1 multiplied by V plus C2 multiplied by V. Okay. Now we easily substitute the values. We know C1 and C2. So we get this as C E minus V is equal to V plus twice V. So this comes as 3 times V, and we can just manipulate the equation and we get this as V we can take common, so this comes as C plus 3 is equal to C times E. So we found out that our potential V will be equal to C times E multiplied by 3 plus C. So the potential at C1 is our V, and at C2 is also our V, because it is V minus 0. So from here we can write our charge Q2 will be equal to C2 minus V. We substitute value of V, we get this as C2 is given to us as 2 microfarad. So this comes as 2 times CE divided by 3 plus C. Okay. And we need to find out our Q2. So we can just rewrite this as Q2 will be equal to twice E divided by, this comes as 1 plus 3 by C. So this gives a relationship between our Q2 and C. Okay. And this C is said to be varied from 1 microfarad to 3 microfarad. Okay. And if we substitute the values, we can easily see that for C1, not C1 but C. So from here we get that our Q2 will be equal to, this will be coming as 2 and is equal to E. We are only interested in the standard values, need not to write the micro part. And from the second we are going to get Q2 will be equal to, this comes as 3, and one second, C is our let me check, this comes as 2E, 1 plus this, 3 plus C. Q2 is our 2E by 2, okay, because this comes as 3 plus 1, 4, and this comes as E. So obviously the charge is going to increase from E by 2 to E, but with a decreasing slope. So we can say that charge increases with decreasing slope. So therefore charge is going to increase and decreasing slope. So option number A is the correct one. Option A is correct. Next question. It was asked in the 2015 mains, and it states that a uniformly charged solid sphere of radius r has a potential V0 measured with respect to infinity on its surface. For this sphere, the equipotential surfaces with the potentials 3V0 by 2, 5V0 by 4, 3V0 by 4 and V0 by 4 have radius R1, R2, R3 and R4 respectively. Then we have to find out what will be the relationship between these, all the radiuses R1, R2, R3 and R4. Okay. So we are given that a sphere is there. So let us draw an approximate figure, and its radius is given as r, and the potential is V naught. So first equipotential surface is given as 3 V naught by 2, and its radius is our r1. Okay. So first of all, let's find out what will be the equation for this V naught, that's the potential on the surface. Then we can proceed further. So we can say potential on surface, which is our V naught, will be equal to kq upon r. Okay. So first equipotential surface is given as 3 V naught by 2. So we are going to make comparison of this 3 V naught by 2 by V naught, and based on this we are going to find out whether this radius r1 will be less than r or greater than r or equal to r. Okay. So first equipotential surface is given as 3 V naught by 2, and obviously 3 V naught by 2 is greater than our V naught. Once again, 1.5 is greater than our V naught. Therefore, we can say that our for the sphere, the equipotential surface has the potential 3 V naught by 2, and this 3 V naught by 2 is having a radius of r1. So let me write the generalized formula for that, and we know that potential inside a uniform charge sphere potential for let me write it here. Potential for uniformly charged sphere and uniformly charged sphere when the point is inside. So we can write this as V of r is equal to kq upon 2r, and this comes as 3 minus r square upon capital R square, and this relationship is going to hold for r is less than equal to capital R, and point outside. And for point outside the sphere, we can write this as V of r will be equal to kq upon r, and this is going to hold for r, small r is greater than our r. And on the surface we have written that is our q upon r. Okay. Now let us go to the given things. So first we are given that we are having first value is our 3 V naught by 2, and this potential is greater than V naught. So therefore the point equipotential surface will be closer to the center. So from here we can say R1 is inside the sphere, because the potential at this particular point, which is given by a radius of R1, is greater than V naught. So obviously the point has to be closer to the center. Therefore we can use our, let us put this here, equation number 1 and equation number 2. So we can use equation 1. So you can say from equation 1 you can write this as 3 V naught by 2 is equal to KQ upon 2R. This comes as 3 minus, and here we are having R1 square upon R square. Yes. And we can easily substitute value of our V naught. So this comes as 3 by 2. V naught is our KQ upon R is equal to KQ upon 2R, and this comes as 3 minus R1 whole square, and this is our R square. K, Q, R and R, 2 and 2 cancel out, and this gives us that our 3 is equal to 3 minus R1 square upon R square. So R3 and 3 also cancel out. So we get that our R1 is equal to 0. Because R cannot be equal to 0, so we get R1 is equal to 0. Next is for our 5 V naught upon 4, which is also greater than V naught. Therefore R2 is inside the sphere. So once again we are going to use equation 1. From equation 1 we write this as 5 V naught by 4 is equal to KQ 2R, and this is our 3. Now radius is our R2, and divided by R square. V naught we already know, we substitute the value, and we get this as 5 upon 4 KQ upon R is equal to KQ 2R 3 minus R2 square upon R square. KQR cancel out, 4 goes by 2, and this gives us 5 by 2 is equal to 3 minus R2 square upon R square. So from here we get our R2 is equal to R divided by square root of 2. Now we come to the third one, that is our 3 V naught divided by 4, which is less than V naught. Therefore R3 is outside. So we are going to use equation 2. Equation 2, we get this as 3 V naught divided by 4 is equal to KQ divided by R3. V naught we already know is 3 KQ upon 4R is equal to KQ upon R3, Here KQ cancels out, so we get our R3 is equal to 4R divided by 3. Finally, for the last part, that is for R4, we are given that our V0 by 4, which is obviously less than V0, so therefore R4 is outside. And using equation 2, we get V0 by 4 is equal to KQ upon R4. Substituting V0, this is 1 upon 4. KQ upon R is equal to KQ upon R4. KQ cancels out, so we get R4 is equal to 4 times R. Now we can easily compare the relationships. Okay. So first we get our R1 is equal to 0, therefore at least option A cannot be correct one, because R2 is not R1 not equal to 0. Okay. And these two are one of the options. Then now we are going to find out our R2. Okay. This will be giving us, so R2 we are also going to find out our R4 minus R3 basically. So we find out our R4 minus R3. So we say R4 minus R3 is equal to 4R minus 4R by 3, and this comes as 8R by 3. And our R by 2 is our R upon square root of 2, which is approximately 0.707 times R. And this R4 minus R3 is approximately equal to 2.667 times R. And our R2 is our 0.707 times R. So therefore we can say that our R2 is less than R4 minus R3. So option number D is the correct one. Option D is correct. Next question. It was asked in the year 2015 advance, and it states that a parallel plate capacitor having plates area S and plate separation D has a capacitance C1 in the air. When two dielectrics of different relative permittivities E12 and E24 are introduced between the two plates as shown in the figure, the capacitance becomes C2, then the ratio of C1 and C2 is. So basic figure is given to us. Here we have two dielectrics, and this having dielectric constant E2 and E1. Okay. And this we can just modify a little bit, and let us extend in this way. We are going to call this capacitance as one second. two dielectrics of primitive this and this between two plates, the capacitance becomes C2. Okay, ratio of C1 and C2 is to be found out. So we are going to call the capacitances, let us call this capacitance as C10, and this is our C20, and this is our C30. And the C10 and C30 are going to have same dielectric, that is our E1. C20 is going to have a different dielectric, that is our E2. But here this C10 and C20 are in series, and that will be parallel with C30. So we can just draw equivalent for that. This is the equivalent circuit. So this is our C10, and this is our C20, and this is our C30. So here C1 and C0 are in series, that is combination parallel with C30. Now we can just easily find out the capacitances. So we can say our C10 will be equal to dielectric constant E1 is given as 2, so this comes as 2 epsilon naught, and the area is S by 2, and the distance is our D by 2. So we get our, this will be equal to 1 second. This distance is D, and okay, here the distance is, let me draw it. The distance between the plates is D by 2, and the surface area is, okay, so this comes as D by 2, and here we are having as even dielectric, and surface area is our S by 2. Okay, so even dielectric is about 2, so this comes as 2 E naught S by 2, and yes, so here 2 and 2 cancels out, so this comes as 2 E naught S divided by D. And next is our C20. C20, the dielectric is 4, so this comes as 4 E naught S by 2, and this is our D by 2, and this will be coming as 4 E naught S divided by D. And we have our C30, and this C30 will be equal to, the distance is D and the area is S by 2, and dielectric is 2, so this comes as 2 epsilon naught, area is S by 2, and distance is D, so this comes as E naught S by D. So we found out the respective their capacitances. Now C10 and C20 both are in series, so we can find out their equivalent. So we can say our 1 upon C equivalent will be equal to 1 upon C10 plus 1 upon C20. And so from here we can say our C equivalent will be equal to C10 multiplied by C20 divided by C10 plus C20. So we get our C equivalent will be equal to C10 was our 2 epsilon naught S D. This is 2 epsilon naught S divided by D, and C20 was 4 epsilon naught S by D. And in the denominator will be coming as 2 epsilon naught S by D plus 4 epsilon naught S by D. And we can take epsilon naught S by D as common. So one of this will be coming as epsilon naught S D whole square, and this is our 8 divided by this comes as 6, and we have epsilon naught S by D. Square goes by this entire term, and we are left with 8 by 6. 8 by 6 we can say this goes by 3 and this goes by 4. So therefore C equivalent will be equal to, this comes as 4 by 3 epsilon naught S by D. So now we can just redraw the circuit. That will be like this. So we have this as C equivalent, and this is in parallel with our C30. And let us call this as prime for the sake of convenience. This is prime, this is prime. And now C30 and C equivalent prime are in parallel. So their equivalent capacitance, we can say our C equivalent will be equal to C equivalent prime plus C30. And here we have 4 by 3 epsilon naught S by D plus C30 is our epsilon naught S by D. So we get taken LCM. 4 by 3 plus 1, that comes as 7 by 3 epsilon naught S by D. So this is our equivalent capacitance of the entire setup. So this is 7 by 3 and E naught S by D. And we are given that in the question it is mentioned that when the dielectric is introduced, the entire capacitance becomes C2. So it means this C equivalent is nothing but our C2. So we get our C2 is equal to 7 by 3 epsilon naught S upon D. And C1 is our without dielectric. So without dielectric we can just separation. C1 is without dielectric, so C1 is epsilon naught S upon D. Now we can find out easily the ratio. So C2 upon C1 is equal to 7 by 3 epsilon naught S upon D is equal to epsilon naught S upon D. Here this epsilon naught S entire term cancel out. So this ratio will be equal to 7 by 3. So we get option number D is the correct one. Option D is correct. Next question. It was asked in the year 2015 advance, and it states that the figure below depicts two situations in which two infinitely long static line charges of constant positive line charge density lambda are kept parallel to each other. In their resulting electric field, a point charge Q and minus q are kept in equilibrium between them. The point charges are confined to move in the direction x direction only if they are given a small displacement through their equilibrium position. Then the correct statement is or are. So basically it is about weather, about their SHM and their direction of the motion. All the options are like that only. So we are given 2. So let us call this as 1 and this as 2. And the only difference between them is that in the first case the charge is plus q, second case the charge is our minus q. And we are given that this is in equilibrium, and let us suppose the distance between the plates is 2d in both the cases. Therefore, on the each side we are going to have a distance of d. So in the first case, in both the cases, it is said it is given a small displacement about equilibrium. Okay, so let us consider case 1. And here we have two plates. Distance between the two plates is about 2d, and the equilibrium position is somewhere here. And let us suppose it is displaced by a small amount by x, and this was our d. Therefore, and this was also our d, and this is lambda and this is also lambda. So new position, this distance will be coming as d plus x, and from the other side the distance will be coming as d minus x. And we are given that they have a positive line charges. Okay, so this is positive as well as this is positive. So obviously, and the charge q here is also positive. Okay, so this charge is positive. So there will be obviously force of repulsion. So let us call this as line 2 and let us call this as line 1. So line 2 is going to apply the force in this direction, and line 1 is going to apply force in this direction, and it is going to move in only one direction. Okay. So obviously the distance between the charge and line 2 is more. Sorry, distance is less, so force applied will be more. So if here the force is our force F2 and this is applying force F1, so we can say net force let us call this as F net 1, or for the sake of simplicity let us call this as F net prime. So F net prime will be equal to our, so this is our x-axis, so F2 will be in this direction, that is our minus of I, and our F1 will be in this direction, that is our plus of I. Okay, so this will be our F1 and this is going to our F2. So we can just add them by using this notation. So we get our F net prime will be equal to, this comes as 2k q lambda divided by d plus x, and d plus x is in our plus I direction, plus then it comes as 2k q lambda upon d minus x, and that is in minus I direction. So we can write this will be equal to, numerator is same, only we are going to write denominator, and this will be coming as 2kq lambda. I we can take as common, so we are left with this as d plus x and minus 1 upon d minus x. So the LCM will be giving us d square minus x square, and it will be coming as d minus x upon minus of minus, and this will be our minus. So this comes as 4k q lambda upon d square minus x square, and giving us minus of I. And it is for our x, if it is very much less than d, therefore we can write our net force will be equal to 4k q lambda, and here I forgot to write x, and this is our x, and divided by d square. Okay, and we have a minus of I. Therefore from here we can say that our net force prime is proportional to negative of the displacement, or in terms of acceleration also in the opposite direction. Okay. So therefore it is going to act as a SHM. Okay. So we can say executes SHM. So plus Q executes SHM. So plus Q executes SHM, plus Q executes SHM. Yes, so both charges. Okay, so at least plus Q execute SHM. So either it will be D is not possible because it says continuous move in direction, and both charges move in direction, so this is also not possible. So only either A or C or both can be true. So we have to find out whether what happens for the minus Q. And similarly, if we so this is our line 1 and line 2, this is our distance D as well as distance D. Suppose it is moved through a distance of x once again. So from here the distance becomes our D plus x, and from here the distance becomes D minus x. Now we have to remember that the charge is negative, so it is going to attract in this direction. Let us suppose is our F2, force of attraction, and it is going to attract with the force of F1. But charge Q1 is much closer to F2, therefore we can say our F2 is greater than our F1. Because of this opposite charge, it will continue to move in x direction. So we can say no SHM, charge that is minus Q moves in x direction. And so option A is incorrect, only option C is the correct one. Option C is correct. Next question. It was asked in the year 2015 advance, and it states that An infinitely long uniform line charge distribution of charge per unit length lambda lies parallel to y-axis in yz plane at z is equal to root 3 a by 2 see figure. If the magnitude of flux of the electric field through a rectangular surface ABCD lying in xy plane with its center at origin is lambda L divided by n epsilon naught, where epsilon naught is the permittivity of the free space, then the value of n is. So we are given that we have a rectangular surface and whose one side is A, other one is L, and it is in xy plane with its center at origin. And there is a line charge whose distance is given as from the y-axis, or we can say center of this plane is given as root 3 2 by A. And this is charge per unit length is given as lambda for this, and the value of the flux that is associated with this rectangle is given as this. So we have to find out the amount of flux that will be associated with the rectangular loop ABCD, equate with the given term, and then we are going to get value of n. So in this case, let us draw a, you can say, hypothetical circle which will be consisting of this, a part of this particular loop, and this is center O, and we have a length that is our AD, and let us join the respective points, and this midpoint is, let us suppose, given as M. So AD is given to S as A, and so AM will be equal to our A by 2, and MD will be also our A by 2. Okay, and the angle formed at the center will be our 30, and this will be also our 30. Okay. So from here we can easily find out our MO. So we can say our MO is given to us as, okay, in this case we have to remember that the line charge is passing through the, it is from this side, this from this side, okay, and the line charge is passing through this point O and is perpendicular to the plane of the paper, perpendicular to plane of paper. Okay. Therefore the distance, this MO, okay, so this is our point O, and from the side if we look, this point will be our M. Okay. So we get our MO will be equal to our root 3 divided by 2, and this is multiplied by A, and we have our AM is our A by 2. And we can find out the angle AOM will be equal to tangent inverse of AM upon OM will be equal to tangent inverse of AM is our A by 2, MO is our root 3 2 by A, which comes as 30 degree, which we can easily see also. Okay, and this is our Gaussian surface, hypothetical surface. So we can say that the flux, according to Gauss law, flux passing through the surface, and that will be equal to, let us suppose our phi is equal to our charge enclosed divided by epsilon naught, and the charge enclosed will be we are only interested in the length L, this length, okay, and which will be in proportion to this only this portion. So this charge distribution will be coming as lambda times L. So Q enclosed will be equal to lambda L divided by epsilon naught. Now we find out that this is through the, okay, and this is basically a 3D diagram, and this surface is not a simple circuit but is like a pipe, or rather we can say cylinder, and we are looking towards from this side. Okay, from this side we are going to get, this will be our one second, this is not O, but this point is our, with respect to this will be our O, and the point on this somewhere here will be our M. So if we look towards from our left side, this cylinder will be coming something like this, okay, and this is with respect to our only AB, AD, and flux passing through the surface, and here surface means whole cylinder. But we are only interested in the flux passing through the plane ABCD. We can say flux passing through plane ABCD, and which we are just representing by side AD will be equal to electric flux passing through the one particular phase, and that is with respect to our angle is our 60 and divided by 360, and the total flux is our phi, which comes as lambda L divided by, this will be our 6 epsilon naught, and the general value of the flux is given as lambda L upon N times epsilon naught. So this gives us the value of N is equal to 6. So value of N is our 6. So this completes all the questions, and these questions were consisting of mains as well as advanced. So from 2014 we solved 1 main question and 4 advanced, and 2015 we solved 2 mains and 3 advanced. So total question we solved are 10. So this complete all the 10 questions. Thank you.